So the next thing after gain calculation is calculating the input and output impedance. So we're going to start with input impedance. Again, we're looking at the common base amplifier. The input is applied to the emitter and the output is taken or sensed from the collector side. To calculate the input impedance, since this is also a small signal parameter, we have to actually draw the small signal first. So I'm going to replace my amplifier, or sorry, my transistor with an R pi and the GM V pi, as always I do. And then the emitter is connected, the input source is connected to the emitter, so this is my VN to ground. Base is connected to this DC voltage source, so I'm going to call it ground. And collector is connected to this RC that is going to VCC, which is a DC voltage source, so that is also ground, right? And remember, these are AC grounds, so like this is not really like ground. These are like basically only ground when we are doing small signal analysis. So I'm going to have an RC here, and for now I'm just going to assume that VA, the early voltage, is actually infinity, so I don't have that R0, right? But if I did, it would have been connected between collector and emitter as we always do. Okay. Now, looking at this circuit, and this is my V out, but I don't care too much about that because the way I actually calculate the input impedance is that I replace the input source with a test voltage. I'm going to call that V test, and then the current coming out of it, I test, right? And I want to find out what is the relationship between these two. Looking at the circuit, I can see that, by the way, this is V pi because we have a GM V pi current source over there. We need to define V pi and its polarity. Now, looking at this, I can see that KVL tells me that V pi is equal to negative VT. I hope this is clear to everyone. You just write a KVL over this path. Okay. Now, knowing this, I can say that, and then I'm going to write a KCL at the emitter node, at this node specifically. So basically, I can say that the current IB, let's call this guy IB, plus IC is equal to IE. So, and let's use small letters. So IB, I can write it as V pi divided by R pi. For IC, I can say GM V pi. And for IE, I can say it's basically negative IT, the test current, okay? So the reason I'm calling it negative is that, well, this is how I defined IE. Now, knowing that V pi is negative VT, I can say that negative VT over R pi minus VT GM is equal to negative IT. All the negatives cancel out. I get VT times GM plus 1 over R pi is equal to IT. Therefore, VT over IT is going to be 1 over GM plus 1 over R pi. Now, if I do common denominator, I'm going to get R pi over GM R pi plus 1. And knowing that this is beta, I can say beta plus 1 is almost equal to beta. So this is almost equal to R pi over GM R pi, which is equal to 1 over GM. Okay. Is this something surprising? Not really. Last week in our impedance discussions, we saw that looking into the emitter, like basically looking into the emitter of a transistor, I knew that if the early voltage is like basically infinity, if there is no early effect, looking into the emitter, I'm going to see 1 over GM. So this is what I've got. So I didn't really like, I wrote it here and I wanted to actually calculate it for you so that you can see how do we actually approach these things again. But we really didn't need to do this. we could have just said, well, looking into the emitter, the input impedance of this amplifier is defined as the impedance looking or the impedance seen by the input source, which is here, right? What kind of impedance looking up we see here is the impedance that we see looking into the emitter of a transistor. We know that that is 1 over GM, especially when there's nothing at the base, and then when early voltage is infinity. Okay, so this is the only, like maybe the only time that we actually write all these equations, but generally I hope that you will, like by the end of last week lectures, you have learned a lot about like how to estimate the impedance or how to calculate the impedance without actually drawing the small signal model, without actually writing all these KCLs and KVLs. This week we're going to practice this a little bit more. And the nice thing about it is that we always, like, no matter if it's a common emitter or common base or common collector, we're always talking about a bipolar transistor, and we're always talking about 3 terminals of that bipolar transistor. So if I'm looking into the emitter and I want to calculate how much impedance do I see from there or how much resistance do I see from there, it doesn't matter what kind of a configuration we are talking about, what kind of an amplifier topology I'm talking about. If I'm looking into the emitter, I'm looking into the emitter, and the resistance that I see is always the same no matter what is the amplifier topology. So this is the simple version of a common base amplifier. We're going to talk about in the next slide, we're going to talk about a more complicated or like a more complete version where we have resistors in the base and, well, other things that to be considered. So here we got 1 over GM simply because there was no resistor in the base. So you can imagine that that's why I could write V pi is equal to VT. If there was some sort of a resistor here, you could have imagined that, well, the V pi wouldn't be VT because that KVL would be different, right? We're going to see about that in the next slide. Now let's take a look at a more complicated example. Here I've added a resistor in the emitter, a resistor in the base. So like things are a little bit more complicated, and we want to calculate the input impedance again, right? Still, I'm assuming that there's no early effect. So early voltage is infinity. Again, my approach is going to be very much the same. So R pi, this is going to be GM V pi, and V pi is defined like this. Emitter is connected to some resistor. I'm going to call that RE, and then there's the input, so I'm going to connect my test voltage V test to here, and I'm going to call this guy I test. Collector is connected to some RC and then to VCC, which is going to be an AC ground, and base is connected to some RB, and then it goes to ground. Okay, now I want to find out what is the relationship between VT and IT. I'm going to start with the same KVL, but then now I know that the KVL is not going to give me V pi equal to VT relationship. The KVL tells me that, so KVL tells me that 0 minus RB times, let's call these currents by their name. So let's call this IB, this is IE, and this is IC. So it's going to be RB times IB minus R pi, oh, let me use black, R pi times IB minus RE times IE minus VT is equal to 0. Okay. Now knowing that IE is equal to IB plus GM V pi times IB, sorry, GM V pi, which is the current, this is really IC, so let me actually write it down so that we have all the steps. IE is equal to IB plus IC, so it's equal to IB plus GM V pi, and I know that V pi is really GM R pi times IB, and then I know that this is IB plus GM R pi is beta, so beta IB, so it's equal to beta plus 1 IB. I could have guessed that anyway. Like I know that emitter current is actually for a transistor that is in the active region is beta plus 1 times base current. But this was a small signal. That is something that we knew for DC, so it would have been nice to actually see it for the small signal as well. Now that I know this, let me rewrite KVL again. So it's going to be minus RB times IB minus R pi times IB minus RE times beta plus 1 IB is equal to VT. Good. Everything is based on IB, so I'm going to write VT is equal to minus IB times RB plus R pi plus beta plus 1 times RE. Now I'm going to replace IB with IT. So I know that IB is equal to, so IB is equal to IE divided by beta plus 1. And I know that IE is negative IT. So it's going to be negative IT divided by beta plus 1. Okay. And therefore, VT is going to be negative IB is negative IT over beta plus 1. So the two negatives cancel out. I'm going to get an IT divided by beta plus 1 times RB plus R pi plus beta plus 1 RE. Okay, and then from here I can say that this is equal to, now I'm going to bring IT on the other to the other side. So VT divided by IT is going to be equal to RB divided by beta plus 1 plus R pi divided by beta plus 1 plus RE. And then knowing that R pi divided by beta plus 1 could be approximated as knowing that, so I'm going to write it here. So R pi divided by beta plus 1 is equal to R pi over GM R pi plus 1. And I can just say that this is really, GM R pi is a big number, so I can actually ignore or neglect plus 1 part, and R pi cancel out, so this is almost equal to 1 over GM, the same approximation that I did before. So this, like the last expression, could be written as RB divided by beta plus 1 plus 1 over GM plus RE. Okay, and that's the kind of input impedance that I see. It might look a little bit complicated. You might think that, well, I'm not going to be remembering that. That's just too long for me to remember. And then you might actually make some changes in the circuit, and then, well, I have to remember a new expression. If you think about it, it's not that there's some sort of a logic into it. And if you remember the logic, then there's no need for you to remember any expression. So if you look at this, what this expression, if you look at the expression, what it tells you is that the impedance that you see, the input impedance is the impedance seen by the source, right, by the input source. So the impedance that you see is RE, the resistance that you see in the emitter, okay? So that was something that we expected, plus, so it almost feels like that this RE is in series with some stuff. So what is those stuff? Let's call them whatever we see from here up, right? So like RE in series with whatever is up there. I know that looking up to the emitter, I'm going to have some 1 over GM. Great. So I got the second component. So what does this thing do there? Well, if you look at here, this term, the term RB divided by beta plus 1, really comes from this resistance here. So it's almost like basically we're saying that we have this RE, looking into the emitter, I have 1 over GM, and I'm basically saying that whatever resistance that you have in the base, divide that by beta plus 1, and now you can say that they're in series with the resistors that are in the emitter, right? If you look at, and then this is very similar, this is identical, or like you can say this is dual of what we discussed in the common emitter amplifiers when we were saying that looking into the base, whatever resistance you have in the emitter, you can make it in series with the stuff that are in the base as long as you multiply them by beta plus 1, right? And you can actually see it here. So when we were writing these KVLs, you can see that the RE, the resistor that is in the emitter, is multiplied by a current that is beta plus 1 times bigger than the resistors that are in the base, right? So it only makes sense that if I want to call all these resistors in series and say that, well, I can just add them up using some like algebraic sum, what I should do is that I have to say that I have to see this resistor beta plus 1 times bigger. Why? Because, well, that's the only way that I can say that these three are in series, because when I say two resistors are in series, I have to make sure that they have the same current, right? So if I have, let me actually draw something here. Let me erase this stuff here. Draw a line here. Okay, so if I have an R1 and an R2, right, and both of them are having the same I can say that they're in series. So like the R total or R equivalent is R1 plus R2. Great. Now, if I have an R1 that has an I, and then I have an R2, and then there is some sort of a branch between them, and I have an R2 that has 100 I. Okay, I cannot say that these two have the same, like since they don't have the same current, I cannot say that REQ is equal to R1 plus R2, right? But I can do this trick that I can say that if I wanted to write the KVL from this point to this point, it would have been, well, R1I, R1, right, sorry. So let's call it VA and VP. So VA minus R1I minus R2 times 100I is equal to VP. Okay, this is equivalent to the same KVL if I had two resistors, that one of them was R1 and the other one was 100 R2, and both of them had the same I, right? Now, for this case, if I want to write the KVL, it's going to be VA minus R1I, R1I minus 100 R2I is equal to VB, right? You see that the same expression appears. VA is the same, R1I is the same, and then here I had R2 times 100I, here I have 100 R2 times I. So from the voltage across the resistor, from the perspective of the voltage that is across the resistor, I can say that because this RE, or whatever resistance that I have in the emitter, has beta plus 1 times more current flowing through it than whatever is in the base, which means the RP and RPi. If I want to write them in series with each other, if I want to consider them in series, if I want to just basically add them up, I have to multiply RE by that beta plus 1. And the same thing is valid otherwise. So like if I want to bring all these stuff to the emitter, I have to divide them by beta plus 1. If I want to say that all of them are in this branch, which has 100 times more current, then because these guys have 100 times less current, these two have 100 times less current, then I have to divide them by beta plus 1. Then I can say that they're in series with the RE, right? So that's why when you're going from emitter, I'm going to summarize this in the next slide. So when you're looking into the base, you're looking from here, you're going to have RB plus RPi plus whatever you have in the emitter times beta plus 1. But when you're looking into the emitter, you're going to have RE plus whatever you see into the emitter, which is 1 over GM plus whatever you have in the base divided by beta plus 1. And then looking at these equations, you would even appreciate that even that 1 over GM is really RPi divided by beta plus 1. So you could have said whatever I have in the emitter plus whatever I have in the base divided by beta plus 1. And what do I have in the base? These are what I have in the base. So RB and RPi. Divided by beta plus 1, they come to the emitter side. I hope this makes some sense. So this is really the summary that I mentioned. So for common emitter, or like it's not that like this is only applicable to common emitter, as I mentioned before. When you're looking into the base, this is the resistance. And well, the reason I'm writing common emitter here is that well, most likely because for common emitter your V in is actually on this side, on the base side you care about this for common emitter amplifier. But let me actually erase it because I don't want you guys to be confused that this is only applicable to common emitter amplifiers. So looking into the base, so looking into the base, what we see is that we see R pi and whatever is in the emitter, which is this guy, times beta plus 1. So that's the resistance that I see looking into the base. And by the way, I've mentioned this before, but I wanted to actually repeat this again. When I say looking into the base, it means that, like the term looking into something, it means that if I put an arrow here and I say, what do I see to the right of this? It means that if I want to replace this with just the same wire on the left of the orange arrow, and then I want to replace whatever is on the right with just the resistor to ground, what would be that resistor, right? So this is really, if I want to replace this with this R equivalent, what would be that resistor? And then this is, well, the resistor is what I've written here. So it's going to be R pi plus beta plus 1 Re. And by the way, remember all of these stuff are small signal resistors. So this is really small signal. It doesn't mean that the transistor can be actually in reality can be replaced with an actual resistor, right? We are saying that if we're in this small signal world, if we're only talking about little perturbations, the behavior of the amplifier, looking into the amplifier, the resistance that I'm going to see is this much. Okay. How about the emitter? You can see that it's 1 over GM that we knew from before, looking into the emitter, plus whatever is in the base divided by beta plus 1. I'm going to add something to this. So I'm going to say that if there was some Re here, then you would have had plus Re here as well. So it's going to be whatever you have in the emitter plus 1 over GM, because we're looking into the emitter, plus whatever you have in the base divided by beta plus 1. And I mentioned in the previous slide as well that this, even in this 1 over GM, is really your R pi divided by beta plus 1. So it's not that like this 1 over GM is some sort of a magical term. It's also part of that whatever you have in the base divided by beta plus 1, right? So this is how you actually look at this is the resistance that you see, no matter if you're doing this for calculating for calculating input or output resistance, right? So like for example, we're going to see that for common collector amplifiers, the output is actually at the emitter. So this is the kind of thing that you actually need for calculating the output resistance. For common base, input is at the emitter, so you need it for input resistance. It doesn't matter why you're calculating it. Looking into the emitter, this is the general form of resistance that you see. Looking into the base, this is the general form of resistance that you see.